Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of the conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of tools of visual image interpretation in remote sensing. Visual image interpretation is the process of identifying and analyzing surface features using aerial photographs and satellite images. Different objects such as roads, rivers, vegetation, settlements, and geological structures appear differently in remote sensing images. Engineers use interpretation techniques to study that images, terrain conditions, land use, drainage patterns, and many more. These methods are extremely useful in highway planning, watershed management, urban development, and geological investigations. Importance of image interpretation, that is the decoding the earth's surface, where raw optical data and interpreted geospatial intelligence. This is the actual comparison. Visual image interpretation is the cognitive process of examining remote sensing imagery to identify and deduct their physical significance. For the civil engineer, an aerial photograph is not just a picture. It is a compressed structural data set waiting to be unzip into actionable site intelligence, just like image number 2. Remote sensing systems collects information through sensors placed on satellites, aircrafts, and drones. These sensors detect reflected or emitted electromagnetic radiation from different objects on the earth's surface. Different materials such as soil, water, rock, vegetation reflect energy differently, creating unique signatures. By analyzing these signatures, engineers can identify terrain conditions, drainage patterns, geological structures, and land use changes important for civil engineering projects. Why civil engineers must read the landscape? That is, process which is initiated with reference to the remote sensing and interpretation technique. At the same time, targeted ground control points are to be mapped based on the data collected, where surface interpretation dictates physical drill placement so that we can study the subsurface components also. Means by using the remote sensing and interpretation, we studied the components on the surface of the earth and also the components below to the surface of the earth with reference to some drilling techniques. At the end, we can design the engineering structures based on some surface and subsurface conditions. So what are the elements of visual image interpretation we are studied? They are based on some tone, shape, size, texture, pattern, shadow, and etc. Here, remote sensing acts as the ultimate reconnaissance tool, where aerial photographs display unsuspected structural features over massive scales. We have to identify these faults and folds, geotechnical, geological components from above dictates or data exactly where expensive subsurface drilling holes are placed, drastically reducing the risk of encountering volatile geology during excavation. Here, one of the precaution, or we can say that the alert, is that automated versus human. So human interpretation utilizing sight and association still outperforms automated pixel classification for complex engineering geology. Means we have to relate the automatic techniques or the advanced techniques with reference to the human activities so that it may create safe and easy survival of the mankind. Cognitive hierarchy of interpretation, the tool where interpretation and identification features based on tone, color, shape, size, texture, pattern, shadow, sight, and association occurred. Here, the pyramid itself suggests that the topmost portion where quaternary level, sight and association, where high level deductive reasoning and environmental context is the second one will be the tertiary level, which is based on the pattern and shadow. That is the complex level, where repeated spatial geometrics and micro topography took place. Third one from the top, that is the secondary level, that is size, shape, texture, where spatial arrangements and boundaries of tone will in picture. And the base primary level, which is based on the tone and color, that is direct spectral reflectance and basic optical physics. The 8 tools of visual image interpretation are not a flat checklist. They form a cognitive pyramid. Analysts build complex geotechnical deductions by first processing fundamental light reflectance, scaling up the geometric recognition, and culminating the contextual deduction. With reference to that pyramid, we can check step by step from primary level to secondary level to tertiary and quaternary. Primary level is depends on the tone and color. On the basis we can visualize the image of the satellite image. Secondly, with reference to the size, shape and texture. Tertiary, pattern and shadow, and at the last, sight and association. So tone refers to brightness differences in black and white images, while color interpretation is used in multispectral imagery. Shape and size helps us to identify road, building, reservoirs and agricultural fields. Texture, pattern and association further improve the identification of landforms and engineering features. The first one, tone and color. Tone refers to the relative brightness or darkness of object in an image. Different materials reflect electromagnetic energy differently or separately, creating variations in tone and color. Water bodies usually appear dark because they absorb most incoming radiation. Vegetation reflects strongly in the infrared region and therefore appears bright in false color composite imagery, just like shown in the picture. Dark tone, early tertiary basalts, that is the rock type, and second one will be the light tone, older gneiss type of rock, where 1000 feet of relief is there. So tone is the relative brightness of an object. Different lithologies or topographical conditions and moisture levels reflect solar radiation differently. A stark abrupt tonal contrast access a landscape in the strongest primary indicator of a major lithological boundary, or we can say that the unconformity, which is a critical warning sign for abrupt shifts in bearing capacity. With reference to the texture in the coastal region, we see the seashore area at the rocks are get fragmented or disintegration will be there. So three images: smooth texture, banded texture and rough texture. Smooth texture, which is due to the fluid or atmospheric conditions. Second will be the banded texture, where parallel strata or layer structure will be seen. And third one will be the rough texture, that is the crushed rock fragments will seen. So texture is the frequency of tonal change across an image created by the aggregation of features too small to be seen individually. A rough visual texture often correlates to highly deformed, fractured and chaotic strata. Remember that texture is strictly scale dependent. What appears rough at 1 meter resolution may appear perfectly smooth at 30 meters while analysis. Texture refers to the visual smoothness or roughness observed in an image. Uniform areas such as water bodies usually show smooth texture, while forest and rocky terrains display rough texture. Shape and the rule of V, that is the pattern, that is natural formation, sinuous or topographic outcrop in the first image, which is shown in the yellow color lines. And second one will be the cultural feature, that is rigid and engineered geometry. So shape distinguishes natural geological formations like irregular or sinuous from cultural engineered infrastructure. It may be rigid or it may be geometric construction projects. In structural geology, shape reveals the attitude of bedrock. As dipping strata cross a valley, their topographical outcrop mathematically forms a shape of V later, immediately telegraphing the subsurface deep, indirect or direct to the remote analyst. So the shape is depend on the different objects possesses characteristics that helps interpreters to identify them. Linear shapes commonly represent road, rivers, railways or canals. Buildings generally appear rectangular or geometric, while natural features show irregular boundaries. The comparison also helps us distinguish between small elements, settlements, industrial zones, reservoirs and agricultural fields. With reference to the size and scale calibration point of view, we can check size is evaluated strictly in the context of an image scale. recognizing the exact dimensions of known reference objects, which allows engineers to extract descriptive geometry or the information. Calibrating size is the prerequisite step or initial step before calculating the true thickness of stratigraphic beds or the depth of rock beds, or estimating the volumetric magnitude of required earthworks. With reference to the size and scale, we check the actual depth, height, or the pattern based on some extrapolated data, reference data, or any related data. The pattern recognition, we can check the spatial arrangements of objects in a repeated sequence. It is the ultimate diagnostic signature of underlying structural controls from the left slip fault or for the right slip fault as per the image explained. For the case study point of view, in the Jura Mountains, recognizing the pattern of Appalachian style faults intersected by diagonal streak slip faults reveals a regional tectonic stress wave that must be accounted for in any large scale infrastructural routing. That is, explains that the fault planes and with reference to the patterns of the rocky layers. It may be with reference to the contours or it may be with reference to the slope or gradients with reference to that area. So patterns refers to the repeated arrangements of objects or features. Urban settlements often show regular geometric patterns, while natural drainage show the systems display irregular patterns. Was the shadow interpretation, the amplification of shadow. Two images are there: high solar angle, that is topography observed, and second one will the micro topography amplified, that is micro topographic condition is seen. So shadow possess a duality. Basically, they obscure data within their footprint, but they aggressively amplify suitable topographic variations. Utilizing imagery with specific low solar elevation angles allows analysts or the engineers to detect fault scraps, ridges, and structural dips that are entirely invisible under direct and overhead sunlight. So the shadows are produced when elevated objects block sunlight. The shape and the length of shadows help interpreters to estimate object height and orientation. Tall structures like buildings, towers, and mountains create prominent shadows. However, excessive shadows may obscure details and create interpretation difficulties and discontinuities in dense urban and mountainous regions. The contextual deductions like site and association. Site where destabilized cliff face, deduction is the gravity sliding, or we can say that a landslide slipping, and association will be the chaotic debris field. Just like to the hilly region and the nearby to the flat region, we can check the site and association domain or tone or visual image interpretation technique. Site, that is the topographic location, and association will be the proximity of related features, which require high level deductive reasoning. An engineer observing a steep cliff face, that is site, directly adjacent to a chaotic rough textured debris field like association, synthesizes these clues to deduce a massive landslide collapse. Context provides the final answer, means at the end we get the output or the answer at the last. So site refers to the physical location and environmental setting of an object. Association means identifying features based on nearby related objects, just like bridges are associated with rivers while ports are associated with coastal lines. This contextual relationship improves interpretation accuracy and support geological and civil engineering investigations. The image processing workflow, which is in the four phases. First will be the detection and last one will be the deduction. So from first detection to recognition, followed by the identification and the deduction. Here in the phase first detection, spotting an anomaly, that is tool which is used to identify or detect the structure, or we can say the feature on the basis of tone and color. Recognition, which follows the categorizing the physical object based on some size, shape and texture. Then identification, do the naming the specific geological features like pattern and shadow. And deduction will be the site and association where extraction of engineering relevance will in picture. So the visual image interpretation tools are divided into four parts where image processing workflow will follow from the detection to deduction. Visual interpretation is not a passive glance, it is a systematic, repeatable algorithm. The analyst moves from identifying basic optical anomalies in the pixels to categorizing shapes, naming the structural geological components, and ultimately deducing the physical limits the terrain will impose on an engineered structure. Primary structural targets. What are the primary structural targets? Three targets are there: strike slip faults, fold system, and angular unconformities. So we will go one by one. Key significance or key signatures or the patterns for strike slip faults are the linearity or offset patterns, just like shown with reference to the river and its path. Second one will be the fold system, which is the subsurface exploration point of view. We can see the repeated sinuous shapes or tonal bending of the rock layers. In angular unconformities, we can mark the key signatures, that is abrupt truncation of pattern, or we can say that the gaps in between the two rock layers. So remote sensing is the mandatory first step in mapping structural geology. Before any desk based calculations for geological components like deep strike or net slip it can occur, the engineer must successfully visually identify the boundaries of faults, folds, and unconformities across the regional landscape for the betterment of the project. Translating pixels into infrastructure routing. Here, the surface interpretation directly detects subsurface concrete. By mapping the surface contact between weak shales and well consolidated conglomerates, interpolating with targeted drill hole data, engineers can safely route deep water supply tunnels entirely within stable bedrock formations, mitigating catastrophic collapse risk. So, with reference to image 1, there will be a drill hole at A, drill hole at B, and drill hole at C. Weak shale zone will be there, which is light blue in color, and the well consolidated conglomerate zone is there with dark blue color, and the third portion will be of the contour images. With reference to that surface map, we have to check the subsurface reality along with that weak shale and well consolidated conglomerate, that the proposed water supply tunnel is there, and so that the whole drill holes like A, B, C may be integrated with reference to the groundwater. That is the translating pixels into infrastructure routing. Means we are taking the image and we are studying that image on the basis of visual image interpretation on the surface of the map and below to the surface of the reality also. Synthesis, that is the interpretation of diagnostic matrix. Diagnostic matrix is actual to the tabulated descriptive format where geological features, primary visual elements, and civil engineering applications are comparatively explained, where geologic features are dependent on the geological components like active fault zone, plunging fold system, unconformity, landslide, and collapse. The each and every visual image interpretation tool is assigned, or we can say that the relate with reference to the geologic feature, just like unconformity, tone, texture, contrast, where the civil engineering application is abrupt changes in bearing capacity of heavy bridge foundations. Means unconformity, which is the geological feature which shown in the imagery, that is tone, texture, contrast point of view, and we can use that data to select the hard strata for heavy bridge foundations or to check the bearing capacity for heavy bridge foundations. Likewise, secondly, for landscape or collapse point of view, site association and texture, just like the region hilly region point of view, or we are doing the tunneling or any roadway construction, then we can go for that, where slope instability will be checked, strict avoidance for highway routing. Visual image interpretation techniques allows engineers to identify and analyze terrain, land use, geological structures, and environmental conditions. Remote sensing provides rapid, accurate, and economical information over large geographical regions. When integrated with GIS, image interpretation becomes a powerful tool for engineering planning and management. So remote sensing and visual image interpretation are essential technologies in modern civil engineering practices. Stay tuned guys. Happy learning.